Hello, this is going to be a quick lecture video for electric potential, and we are going to draw ideas from the ordinary potential energy we know. I believe you did something on potential energy in SHS, so we are going to draw on that understanding to help us understand what potential energy is pertaining to electrostatic fields. So potential energy is defined as mgh, where m is the mass, g is the force of gravity, and h is altitude. This means that potential energy is defined based on the relative position of a body with respect to the earth. So supposing this is our earth, if we place a certain body directly on the earth such that its altitude is equal to 0, then it follows that the potential energy will be equal to 0 because h is equal to 0. Now, if we lift up this body higher to a certain altitude h, which is higher than the ground, then the body is going to now have a different potential energy, a much higher potential energy than it had when it was on the earth. Okay, so this also shows us that there is some amount of work we need to do in order to lift this body against the force of gravity to a certain point, because force of gravity is always acting down to keep the body on the earth. So to be able to move the body from the earth to a certain height above the earth, we need to work against gravity. Therefore, potential energy can also be defined as the work done against this gravitational force, right? And that means, for such a definition, the potential energy is inherently a negative value if the direction towards the earth is seen as a positive value. Now, drawing from this understanding, we can see that in terms of electrostatic fields, supposing we have a certain charge, negative charge, minus q, as we see here, right? So this charge, because it is negative, right, will be attracted to a certain positive charge if that positive charge is within the electric field of Q1. So Q1 certainly has an electric field around it, and any charge that comes within the electric field will either be attracted or repelled. Now, if it is a positive charge like we see here for Q2, which is 1 coulomb, positive 1 coulomb, within the electric field of Q1, Q2 is going to be attracted to Q1, right? So if we intend to move Q2 further away from Q1, from a position of 1 as we have designated here, to a certain position 2, we will need to do a lot of work against the attractive electrostatic force. And that work we need to do is the potential energy, okay, the electric potential energy. Now let's recall that work done is equal to force times distance, and remember we are working against the direction of the attractive force, which is positive, okay? And because we are moving Q2 from Q1, which is a negative charge, right, in the opposite direction, okay, the work done is going to be a negative value, right? Because the distance or the displacement is in the opposite direction. So we will have work done as minus f times the distance dr, a very small distance dr. If we recall, force is equal to k q1 q2 all over r squared, okay? And the electric field is equal to, say, if it is the field for Q1, that is equal to k q1 over r squared. This implies that the force between Q2 and Q1, right, from the example that we have shown so far, will be equal to Q2 times the electric field of Q1. And since Q2 is equal to 1 coulomb, right, then we can say that the force is equal to what? 1 coulomb times the electric field of Q1. So this will be approximately the electric field of Q1 because Q2 is 1 coulomb. Please, let's keep that in mind. We are not saying that the force is equal to the electric field, right? We are just saying that if Q2 is 1 coulomb, then the work done necessary to move that 1 coulomb a certain distance away from the electric field, right, is approximately the magnitude of that electric field because Q2 is equal to 1 coulomb. Okay, so if that is the case, then we can say that the work done is now equal to minus the electric field times the R, okay? Because Q2 is equal to 1 coulomb. All right, so now replacing the work done with the potential energy, because that is what we are actually working with, then that potential energy, right, for any short distance is equal to EdR. Now, if we are able to measure the potential energy for every minute distance we move the Q2 away from Q1 through, right, then we will have the sum of the potential energies over that distance, okay? So then we can find the integral, right? Now we are using the integral sign. We are integrating, or we are adding up minute potential energies for each short distance, okay? That is the meaning of the integral. So because of the summing over the short distance, we are integrating over a longer distance, right, based on the tiny bits of distances within that long distance between D1 and D2, right? So we say that V12, which is the potential energy from the position of 1 to the position of 2, is equal to the integral, okay, which is the sum of the tiny bits of potential energy from D1 to D2, so EdR. Okay, so let's remember that E is equal to KQ1 over R squared, but Q1 is negative, right? So this means that E will be equal to negative KQ1 over R squared, right? Remember that the electric field is for Q1 from our example. And so the potential energy becomes minus the integral from D1 to D2 of minus KQ1 over R squared dr, right? Giving us a positive KQ1 because K is a constant and the integral is not being taken over the Q1. And so K and Q1 can come out of the integral so that we will have only 1 over R squared dr from D1 to position D2. Okay, so the integral of 1 over R squared, right? First, let's remember that 1 over R squared is equal to R to the power minus 2, okay? So it means that that integral is going to be like the integral over R to the power minus 2. And when we take the integral of that, what happens to the R? The order minus 2 is summed with 1, and then we divide it by minus 2 plus 1, so that it gives us what? R to the power minus 1 over minus 1. And this is equal to minus R to the power minus 1. R to the power minus 1 is what? 1 over R. So this becomes minus 1 over R. Okay, so we are going to put that into the integral here. This equation, let's call that equation star. So putting this, substituting it into equation star, right, we are going to get V12 as what? KQ1 then times minus 1 over R from D1 to D2. So usually this should be KQ1, then we have what? 1 over D minus 1 over D2 minus 1 over D1, okay, because this negative flows through all, okay, or let's just say it this way so that it would not confuse anyone. So minus into brackets 1 over D2 minus 1 over D1, right? So this becomes KQ1 minus 1 over D2 minus 1 over D1, which is then what's KQ1 then minus 1 over D2 plus 1 over D1, okay? So this implies that we can rewrite this as V12 is equal to KQ1 then what? 1 over D1 minus 1 over D2. And that is our potential energy. So as we see here, we have KQ1 over D1 being equal to V1, then KQ1 over D2 being equal to V2. Okay, so the potential at a position V2 is given as KQ1 over D2 with respect to Q1. Then the potential with respect to Q1 at a position D1 is given as V1. And the potential difference, which is voltage, the potential difference between the two is equal to V1 minus V2. Okay, now let's try this example that says that find the absolute potential of an isolated point charge of 10 microcoulomb at a distance of 0.2 meter and then 10 meters, and then hence determine the potential difference between the 2 points. So this is quite simple. So Q1 is equal to 10 microcoulomb. Then at a distance D1 of 0.2, we have V1 to be equal to K is what? 8.99 times 10 to the power 9 times 10 microcoulomb, so times 10 to the power minus 6 divided by D1, which is what? 0.2. So this will give us 449.500 times 10 to the power 3. Then V2 will be equal to 8.99 times 10 to the power 9 times 10 times 10 to the power minus 6, all divided by 10 meters. Okay, so that will give us 8.99 times 10 to the power 3 volts. Therefore, the voltage between the two of them, or the potential difference, V12 is equal to V1 minus V2, and that is 449.500 times 10 to the power 3 minus 8.99 times 10 to the power 3. So this is 440.5 times 10 to the power